Welcome back to the deep dive. Today we've been handed the rulebook, a bill of materials, and a whole stack of design notes for a brand new Formula Student electric team. And they are facing, well, a pretty brutal challenge.
It's immense.
Yeah, our job isn't just to build a fast car, it's to build a reliable system, a world-class competitive powertrain. And all of this is under, crushing deadlines, a limited budget, and absolutely zero tolerance for error, especially when you're dealing with high-voltage systems.
Exactly.
This challenge is huge because it really mirrors the biggest problem in the entire auto industry right now, that global shift to electrification and software-defined cars.
Right.
This student team has to do in 18 months what the big manufacturers take years to develop. So today, we're their strategic engineering consultants.
And that is precisely why let's call it the traditional chaotic build and break it approach is just a guaranteed failure. When you combine the physical danger of high voltage systems, we're talking 400 volts, maybe more, with these super strict non-negotiable rules of an event like Formula Student Germany, you need a professional systemic strategy. So we're imposing the industrial standard right away, the 14.0 V-model development roadmap.
I like that, a commitment to professionalism. This is systematized thinking, right? Straight out of the McKinsey playbook, but tailored for these really complex systems. But for our listeners, why drag a massive industrial framework like the V-model into what is essentially a university garage project? What's the strategic return on that?
The strategic value is it's entirely in one concept we call shift left.
Shift left.
Yeah. If you picture the V model, the left side is all your design, your planning, breaking down the requirements. The right side is all about putting it together, verification, testing. And the simple, brutal truth is this. The earlier you find a flaw, the further left on that V, the cheaper it is to fix.
Okay, that makes sense.
I mean, think about the math. A logic error we find during the system requirements review, the SRR phase, which is just pure documentation, that costs basically nothing to correct, maybe an hour in a meeting, a change in the spreadsheet.
Right.
But that same exact flaw, if it makes it all the way to track testing, the far right side of the V, now you're talking physical rework, maybe sourcing a new inverter, wasting thousands on track time and months of delay. Our sources show that fixing problems late can be dozens, maybe even hundreds of times more expensive.
So the V model is really about discipline. It forces us to define the test and the verification before we even design the component. It strategically moves risk away from that expensive, dangerous, real-world physical testing.
Yes.
And puts it into affordable virtual validation. So we're talking model-in-the-loop, hardware-in-the-loop testing.
Precisely. Our mission today is to walk this new team through those 7 critical phases, from SRR, the strategic requirements, all the way to rollout, track validation. And we're going to have a laser focus on compliance, reliability, and safety. For a rookie team, finishing that 22-kilometer endurance event fault-free, that's a far greater strategic victory than, chasing some impossible world record in acceleration.
Reliability over raw, risky performance.
That's the mandate for year 1.
Okay, let's dive in.
We begin with phase 1, the System Requirements Review, or SRR. This is our foundation. And we start with the absolute non-negotiable red line. Total compliance with the competition rules. If you've failed technical scrutineering, your season is over before the car even turns a wheel. We have to start there. The rulebook isn't a guideline. It's the absolute boundary of our design space.
And those rules are always evolving, right? Especially as battery tech progresses. So looking at the latest 2026 FSG rules, where are the critical technical hurdles that a new team might just completely overlook, especially in the battery design?
The biggest headache right now is definitely the increased stringency around cell temperature monitoring. That's in sections EV 5.8.5 through 5.8.7. And this isn't just about sticking a sensor somewhere in the box anymore.
Okay.
The rules are really tightening the definition of where that sensor has to be. Historically, some teams could get away with placing sensors, near the main bus bar connection, maybe 10 millimeters away, just assuming that was the hottest point.
But that assumption is proving to be, dangerous?
Absolutely. The new trend, and we're seeing this in rules updates globally, is a move toward requiring direct physical contact with the cell's negative terminal, or a confirmed thermal hotspot that you've proven with simulation. They're forcing the monitoring to the location most likely to show an internal fault early.
That sounds like such a minor tweak, but I'm guessing the impact on manufacturing must be massive, especially for the kind of cells these student teams use.
It creates a huge manufacturing headache. Most new teams, they start with common cylindrical cells like 18650s or 20100s. They're robust, they're available, But the design flaw here is that the negative terminal is often the entire steel case bottom of the cell, and that's usually packed tightly inside the module structure, for mechanical protection.
Right, it's hidden.
It's hidden. And trying to reliably fix a sensor directly onto that hard-to-access terminal, it forces a radical rethink of the whole module design.
So we can't just rely on a thermistor sticker glued to the side of the cell's wrapper anymore.
No, that method is now non-compliant. To get reliable contact on that negative end, it often forces you to use flexible printed circuits, FPCs, that have to wrap around the module, or it requires a really advanced glueless mechanical design that lets you get access for the sensor. This immediately drives up complexity and cost. And if a team decides to buy commercial off-the-shelf modules, COTS, to save time, they have to demand verification from their supplier that the sensor installation meets these new specific terminal contact rules. It's a perfect example of a level 1 rule cascading down into a level 3 physical manufacturing requirement. It proves why SRR is so critical.
So beyond temperature, we have to lock down the basic definitions. The moment the orange cables appear in the design?
Yes. The definition of high voltage, or HV, has to be set immediately. Anything over 60 volts DC or 25 volts AC RMS. The second you cross that line, you trigger a huge cascade of mandatory safety requirements.
So that's the orange cabling we see.
That's the bright orange cabling, specific physical protection ratings IPXXB or IPXXD to prevent you from touching live parts with a finger or a tool, mandatory physical locks on connectors, and clear HV warning labels all over the chassis. You can't proceed without that.
And then there's the nervous system of that HV safety, the insulation monitoring device, or IMD. This is what decides if the car is even safe to touch, especially after a crash or in the rain.
The IMD is crucial. It has to continuously monitor the electrical resistance between the high-voltage system and the chassis ground, which is the low-voltage system ground. And the FSG threshold is tough. The insulation resistance has to be greater than 500 ohms per volt across the whole system.
So maintaining 500 ohms per volt means we're not just relying on the box itself, we're building continuous active monitoring into the very integrity of the system, like down to how tight our connectors are.
Exactly. This one requirement dictates the quality of every single millimeter of wire insulation, the integrity of every connector seal, and the robustness of your whole accumulator enclosure. If your insulation fails, even just a little, from chafing or water getting in, the IMD detects that resistance drop and triggers a mandatory shutdown. It forces you to think about sealing right from the start.
Okay, so once those safety guardrails are set in the SRR, we have to translate the rules and the goal of just finishing into actual numbers, performance targets. And that's where lap time simulation, or LTS, comes in. This is how we move from a vague idea of fast to a precise definition of world-class competitive for our car.
LTS gives us those quantitative targets. We use sophisticated models, quasi-steady state, point mass models, to run sensitivity analyses. This tells us where to put our engineering effort for the biggest performance return. And year after year, the simulation proves the same thing for electric Formula Student cars. Mass sensitivity is the critical lever. It's far more important than marginal gains in motor power.
How sensitive are we talking? Like, what does a kilogram of weight reduction actually get you in lap time?
It's extremely sensitive. High-fidelity simulations consistently show that every single kilogram you can shave off the vehicle can cut between 0.01 and 0.03 seconds from a typical lap time. And since the battery is the single heaviest component, its design, its energy density versus total capacity becomes the primary driver of the car's performance and handling.
So the simulation tells us exactly how big the battery needs to be for the toughest event, the 22-kilometer endurance, but it also tells us how small we can possibly make it.
Yes, exactly. That 22-kilometer run defines the minimum usable energy capacity. That usually falls somewhere between 6.5 and 7.5 kilowatt hours for a team targeting high efficiency. But, and this is critical, LTS lets us model the energy management strategy before we build the car. If the team can implement effective regenerative braking region, the simulation can confirm that this software feature might recover, say, 10 to 15% of the energy used.
And that recovery directly reduces the battery size needed.
Directly, which translates to a lighter car and better lap times.
Yeah.
It's a virtuous cycle, and it's defined by software validation, not by just buying a bigger motor.
So let's lock in some key performance indicators, some KPIs for this new team. We need targets that are ambitious, but also pragmatic, prioritizing finishing over flash.
We have to be pragmatic. I mean, top teams like AMZ Zurich have hit spectacular world records in acceleration, dipping below 1.5 seconds for 75-meter liters. But our year one goal is guaranteed completion. So we'd recommend an acceleration target of under 4.0 seconds for that 0 to 75-meter event. A reliable finish guarantees you huge points. A risky, aggressive attempt that ends in failure loses everything.
And weight?
Weight targets are critical. We'd target under 280 kilograms for a single motor setup, or maybe under 300 for a dual motor setup, and that includes the driver. This forces the team to make weight-conscious choices on everything.
But what's the one single overarching metric that really proves the maturity of the system?
The reliability metric. The team must complete 100 kilometers of continuous fart-free testing mileage. I cannot stress this enough. Our sources confirm this is where most new teams, even the ones who build a car that looks fast, ultimately fail. If you haven't put 100 kilometers on that system without an electrical fault, a thermal trip, or a communication error, you are not ready to compete.
And finally, to link this all back to that professional V-model framework, we have to talk about traceability. The Requirements Traceability Matrix, or RTM. This is the spine of the whole strategic document, right?
The RTM is how professional engineers manage complexity. Every single rule or user need, that's level 1, like the accumulator must not breach at 40G, must link directly to a system specification, level 3, like the TSAC material is 6061 T6 aluminum, 4 millimeter thick. And that, in turn, has to link to a specific test case, level 4, maybe an HL simulation or a physical test. This structure means that if a judge questions a design choice, the team can immediately trace it back through the RTM to the specific rule it satisfies. It's proof of compliance and risk mitigation.
Okay, we've cleared SRR, constraints are set, KPIs are quantified. Now we move to phase 2, the concept design review, or CODR. This feels like the big strategic pivot point. We're moving from what do the rules demand to what architecture will best meet those demands with the least amount of risk.
And the single most critical decision here, the one that locks in about 80% of the complexity for the entire year, mechanical, electrical, and controls, is defining the powertrain topology. We have to choose wisely and avoid the temptation of maximum performance at the cost of, well, existential risk.
Let's break down the big topology trade-offs then. We've got 3 main paths. First up, the high-risk, high-reward option, the 4WD hub motor.
This is the pursuit of ultimate performance, right? The advantages are phenomenal on paper. Ultimate torque vectoring for perfect cornering, flexible center of gravity, great packaging. But for a new team, those advantages are seductive traps.
Traps? How so?
They introduce 2 what I would call fatal flaws. First, the mechanical problem, massive unsprung mass. Putting the motor right inside the wheel assembly just kills your suspension response and handling predictability. Second, the controls problem. I mean, the complexity of managing 4 separate electronic differentials and ensuring stable torque delivery across 4 different tires, it's immense. Teams like AMZ, who've set records with this, have nearly a decade of collective experience refining those algorithms. For a new team, the risk of controller failure or a software bug is just too high. So my strategic advice is highly not recommended. This choice practically guarantees a high probability of not finishing.
I get the technical risk, but isn't settling for less than 4WD basically an admission that we're sacrificing ultimate performance? How do you justify that to a team that's eager to push the boundaries?
You justify it with a reliability metric. A world record means nothing if you can't pass scrutineering or finish the endurance event. For year 1, you need a stable platform to learn on, which leads us to the simplest, most robust option, the 2WD single motor rear drive.
The workhorse.
This is the anchor topology. It's the simplest system, lowest cost, and it uses a mature mechanical structure, a single inverter, a robust motor, and a simple chain or gear drive with a mechanical differential. The control strategy is straightforward. You sacrifice advanced torque vectoring, but you maximize completion and reliability. Strategic advice. Highly recommended. This is the best way to hit that 100-kilometer reliability target.
Okay, and then there's the compromise, right? The 2WD dual motor setup.
This is a decent intermediate path.
Yeah.
By having 2 independent motors on the rear axle, you get rid of the heavy mechanical differential and you gain electronic differential capabilities. It's good for packaging, a little better for low-speed cornering. However, it instantly doubles your inverter count and introduces medium complexity and control. My advice here is it's viable only if the team already has strong, proven electronics and controls expertise. Otherwise, stick with the single motor.
So with the architecture set as a single motor rear drive, we turn to the electrics architecture, batteries and voltage. This is where chemistry meets packaging. Let's start with the cell selection. Cylindrical versus pouch.
Yeah, clear pros and cons to both. Cylindrical cells, 18650s, 21700s, they offer great mechanical structure, a stable supply chain, and, crucially, easier thermal management because you can flow coolant through the gaps between them. The big con is assembly. You're dealing with hundreds of individual parts, which means hundreds of precision welds.
Pouch cells seem like they'd solve that assembly problem, and they're more energy dense.
They do offer superior energy density and lower internal resistance, yeah, but the cost is paid entirely in mechanical risk. Pouch cells are soft. They need precise external pressure plates, complex welding like laser or ultrasonic, and they're extremely susceptible to puncture, damage, or swelling.
Wait, so the real strategic insight here isn't just that pouch cells are mechanically tricky, but that they introduce a single point of catastrophic failure that a new team just can't risk.
Absolutely. The thermal and mechanical containment of a pouch cell module is immensely complex. For a new team, the packaging risk, just trying to meet the safety standards, makes the pouch cell a massive strategic liability.
So what's the recommended path?
The recommended path is cylindrical cells, the 18650s or 21700s, paired with a glueless mechanical module design. This makes maintenance way easier, and critically, it simplifies installing those temperature sensors to comply with the new rules. Alternatively, if time is your biggest enemy, a team should seriously consider buying COTS modules from a good supplier. They're more expensive, yes, but they save months of high-risk development time and come with pre-compliant stocks.
Okay, next up, the voltage platform. The rules allow up to 600 V, and the top teams push that limit. What's the strategically sound choice for year one?
This is a classic reliability versus performance decision. I strongly recommend the 400V platform, typically rated for 350 400V. While it's true that top teams push to 600V to minimize current loss, which reduces cable weight, high voltage dramatically increases insulation requirements, the complexity of the shutdown circuit, and the cost of all your test equipment.
I get that 400V is safer and has better component availability, but the AMZ car, the record holder, runs at nearly 600V. Isn't choosing 400V an admission that we're leaving performance on the table?
It's an admission that we are prioritizing reliability and compliance in year one. The 400V platform hits the sweet spot. Component availability is abundant. Industrial 600V or 1200V IGBTs and 6-sample devices are easy to source. More importantly, the cost and safety training for handling a 400V system is far more accessible than for a true 600V system. We aim to finish the race this year. We can aim to maximize performance next year, once that reliable foundation is set.
Okay, so with those concepts defined, single motor, cylindrical cells, 400V, we get to phase 3, the preliminary design review, or PDR. This is where we have to freeze the physical design and translate those simulation results into actual hardware.
This is where we stop talking and start sizing components. We iterate on the LTS data to pick the motor and inverter. If our target is a reliable 3.5 seconds from 0 to 100 kOPH, the simulation tells us we need a peak power of roughly 80 kilowatts. That number drives the entire component selection.
And since we're racing on tight tracks, max speed is pretty low, maybe 110, 120 kOPH. How does that affect gearing?
It means the gear ratio has to be biased heavily toward acceleration, so you need a higher reduction ratio. This increases wheel-end torque, which is far more valuable on a Formula Student course than a high top speed you'll never actually reach. Gearing for 180 kph is just sacrificing points.
Thermal management also has to be frozen at PDR because it impacts packaging and weight so much. What's the lowest risk approach for a new team?
For a new team, if they select cells with a large current overhead and wide temperature tolerance, air cooling is the first choice. It's simple, it's lighter, and it eliminates the massive complexity of pumps, radiators, coolant, and the risk of leaks, which is an automatic scrutineering failure. If the team absolutely has to go with liquid cooling for high C-rate cells, they must complete detailed sizing calculations at PDR. Otherwise, they risk massive heat duty rating during the endurance event.
And finally, the PDR centerpiece, the HV single-line diagram, the safety blueprint.
This diagram is non-negotiable. It has to precisely detail the topology of all critical safety components. This includes the accumulator isolation relays, the AIR-AS, two massive contactors on both the positive and negative sides of the pack, and crucially, it has to include the pre-charge circuit.
Can you break down the pre-charge circuit? It sounds simple, just a resistor, but it prevents a catastrophic failure.
Without that pre-charge resistor and its relay, the entire 400-volt pack hits the massive capacitors in the main inverter with no resistance. That sudden jolt of current is called inrush. It's so violent it can generate sparks, damage the inverter, and most commonly, it's powerful enough to permanently weld the contacts of your main relay closed.
And if that relay is welded shut,
You have no way to shut off power from the battery. It's a massive safety failure. The pre-charge resistor just limits that current spike, letting the capacitors charge safely before the main AR closes. The diagram also has to include the high voltage disconnect, the HVD for manual shutdown, and correctly sized fuses inside the battery box with sufficient braking capacity for a worst-case short circuit.
We've made it to Phase 4, the Critical Design Review, or CDR. The design is frozen, it's ready for production. This is the big gate review, and the key deliverable is the Finalized Electrical System Form, the ESF. This is the team's ticket to actually compete.
The focus now shifts entirely from concept to absolute meticulous safety detail. We have to eliminate any possibility of a catastrophic failure. And the most critical system, the most common failure point in scrutineering, is the shutdown circuit, the SDC. It is the electrical lifeline of the car.
Let's get into the SDC's required logic. We know it has to be robust, but what does that mean in terms of, physical implementation versus software?
The SDC must be a physical, series-connected logic loop. Think of it like a chain of dominoes. Every single safety condition has to be met for the power to stay on. If you interrupt any component in that series loop, any domino, it has to instantaneously cut power to the AR coils, which cuts all drive power. And this function cannot rely on software. It has to be hardwired.
Okay, and what components are in that chain?
It has to have the cockpit e-stop for the driver, 2 external e-stops for marshals, an inertia switch for a crash, the brake system plausibility device, the BSPD, the IMD fault output, the BMS fault output, and the HVD interlock. All in series.
The engineering challenge there with all those components in series must be just ensuring reliability over the length of the car. You've got long wires, connectors, switches.
Absolutely. We have to design against 2 major failure modes. First, the circuit has to be robust against vibration or accidentally shorting to positive voltage, which would dangerously prevent a shutdown. Second, and this is where calculation comes in, you have to meticulously calculate the cumulative voltage drop across that entire loop.
Why is voltage drop so critical there?
We have to ensure that the final AR coil still gets enough pull-in voltage, usually the 12V from the low-voltage system, to reliably activate and hold the contactor closed. If the voltage drops too low, say down to 7V, the coil might just release prematurely during a voltage sag on acceleration. That's a nuisance trip, and it ends your event instantly, even if the car is perfectly safe. You have to calculate and test this at CDR.
Okay, next, let's dissect the BSPD, the brake system plausibility device. This is arguably the most common electrical failure point for rookie teams, mostly because they try to over-engineer it with software.
The BSPD is mandatory hardware that enforces a basic safety rule. If the driver presses the brake hard, A&D simultaneously demands acceleration. So throttle is applied, generating more than 25% demand or 5 kilowatts of power. The system must immediately cut power. It prevents the car from accelerating uncontrollably if a throttle sensor sticks.
And the rules are specific that this has to be non-programmable physical hardware. Why is that?
Because software can fail. It can freeze. It can have latency. Safety-critical functions have to be analog and deterministic. The BSPD must be implemented with non-programmable circuits. Analog comparators, reliable RC delay circuits, latches to ensure the safety function can't be corrupted by a software bug. And you should use simulation, like LT-Spice, during CDR to verify the switching logic, and especially that required 500 millisecond time delay.
Another critical hardware circuit is the TSAL, the Tractive System Active Light, the visual indicator of HV status.
The TSL logic is strictly mandated and has to be fail-safe. When high voltage is active, above 60V, the red light has to flash between 2 and 5 Hz. The implementation has to use a high-voltage divider tapped directly off the HV bus, feeding into an analog comparator, like an LM311. That comparator then triggers a robust timing chip, like a 555 timer, to generate the flashing. It has to be completely independent of the main vehicle controller.
And the green light.
The green light is just as critical. It can only be on when the HV system is safe or discharged. The logic has to verify 2 things. Voltage is confirmed below 60V, and the control logic must verify that the errors are open and the precharge is off.
You mentioned a hidden detail here about PCB safety standards.
A vital detail. For both the BSPD and TSAL, teams must adhere to high-voltage standards like IPC 2221. This dictates physical segregation.
Let's clarify this idea of slotting. You're not just talking about spacing components out, are you?
No, we're literally talking about carving a tiny channel, a slot, into the printed circuit board itself. This slot increases the creepage distance, the distance current has to travel across the surface between the high-voltage parts and the low-voltage parts. We're breaking the path to ensure that current can't jump from the HV side to the LV side, which would fry the control system. Then you use reliable isolators, like optocouplers, to bridge the communication across that physical gap.
Shifting to mechanical safety, the accumulator container, the TSAC, is the final barrier. The structural requirements here are extreme.
They're designed to survive a massive impact. The container has to withstand 40 grams of longitudinal or lateral acceleration and 20 grams of vertical acceleration without the accumulator breaching. The design has to prove this at CDR.
For a new team, material choice for this box is a strategic decision that can save a lot of time, right?
A classic example of simplicity saving time. New teams should use aluminum or steel instead of composites like carbon fiber. Using metal significantly simplifies the structural equivalence sheet, the SES verification. Composites require extensive destructive testing or highly complex validated FEA simulations. Metal designs, supported by clear stress calculations, streamline the paperwork and avoid scrutineering delays that just sink new teams.
And the final key deliverable of CDR, which enforces that shift-left philosophy, is the DFMEA, the design failure mode and effect analysis, the proactive assessment of what could go wrong.
DFMEA is mandatory. It identifies potential failure modes before they happen. You analyze the system, identify a failure mode, assess its severity, occurrence, and detectability, and then you calculate the risk priority number, or RPN. Then you prioritize mixing the things with the highest RPNs.
Give us a specific high-risk example of an analysis CDR has to cover.
Let's take the throttle system. Failure mode, throttle pedal signal wire disconnects. Consequence, uncontrolled full acceleration if the signal floats high. This is a severe high RPN event, so our mitigation has to be layered. It needs dual redundant sensors with software cross-checking and a crucial hardware fix, pull-down resistors on the analog lines.
And that resistor is key because it overrides any potential software issue.
Exactly. The pull-down resistor ensures that if the wire disconnects, the signal voltage immediately defaults to zero, commanding zero torque. We can't rely only on software to catch a disconnected wire. The RPN calculation forces the team to spend time and money where the risk is highest, ensuring the safest possible design before a single part is built.
Okay, we've passed CDR, the design is frozen, phase 5 is manufacturing. Here, the focus shifts to operational quality, supply chain, and execution. And the clock is really ticking.
Procurement of long lead items is a strategic imperative that has to happen immediately after CDR, so months 7 through 10. This is often where rookie teams fail, underestimating commercial lead times. High-performance battery cells, specialized high-voltage contactors, your kilovacs, your gigavacs, and rugged Amphenol connectors can have lead times of 8 to 16 weeks, sometimes longer. If you don't order those parts instantly, you can't start building the battery on time, and the whole schedule breaks.
Once the parts arrive, ensuring quality during assembly, especially the wire harness, is vital. We know wiring failures are probably the most common cause of a DNF in student racing.
To combat this, the team has to adopt industrial standards, specifically IPC-WHMA A620 for wire harness assembly. This introduces standardized quality control. Crucially, teams must prohibit using simple pliers for crimping. You have to invest in specialized, calibrated crimping tools for the specific terminals you're using. And every critical connection has to undergo a mandatory pull test, a physical measurement of the force needed to pull the wire out. If it pulls out easily, it will definitely fail under track vibration.
Let's talk about noise, EMI, electromagnetic interference. High-power systems generate a ton of electrical noise that can scramble sensitive signals.
This requires rigorous EMI mitigation. The high power lines from the inverter to the motor must be shielded cables, and crucially, that shield needs 360-degree grounding using specialized EMC connectors. If that ground path is broken, noise gets into your sensitive CAN bus or analog sensor lines, leading to these intermittent, impossible-to-debug failures where the car just loses communication under heavy acceleration.
We mentioned the battery is the highest risk component. Assembling it has to be the most dangerous activity in Phase 5.
Absolutely. Battery assembly requires the most stringent safety protocols. It has to be done in a dedicated, isolated area with only insulated tools, fire blankets, and D-class fire extinguishers. Only trained electrical safety officers, ESOs, can be present. And you have to follow strict SOPs, including pre-assembly testing, checking the internal resistance and voltage of every single cell before final assembly. A single weak cell can become a hotspot that leads to a cascading thermal runaway during the endurance run. Quality control is safety control here.
Once manufacturing is underway, we shift to Phase 6. Closed-loop validation, the core of the V model's right side, done through hardware-in-the-loop testing or HIL.
HIL is the strategic centerpiece of risk reduction. It lets us safely test extreme faults like high-speed emergency braking, severe overheating, catastrophic communication loss. By replacing the physical car with a mathematical digital twin, we're testing the physical controller, the VCU or the BMS, against a virtual car under conditions we could never safely replicate on the track.
That sounds expensive. Do new teams really need to invest in massive systems like DSpace or SpeedGoat right away?
No. The beauty of this approach is scalability. A new team can build a very functional, low-cost HIL setup. For BMS testing, you don't need to simulate power flow. You just need to simulate cell voltage feedback. A team can use simple resistor divider networks or op-amp circuits to simulate the 100-plus cell voltages the BMS expects to see.
So we're basically fooling the physical BMS hardware into thinking it's connected to a real battery that's suddenly dying or overheating.
Exactly. And this low-cost approach lets us do the most valuable function of HIL, fault injection testing. We intentionally create catastrophe in the virtual world to ensure our physical safety hardware reacts correctly. The goals are clear. First, verify the BMS response. Does the physical BMS instantly trigger the AR shutdown when the simulation injects an overvoltage fault? Second, validate the VCU logic. We test its response to simulated signal noise, a sudden loss of CAN communication, and most importantly, we validate the BSPD logic. We simulate high virtual throttle and high virtual brake pressure at the same time to ensure the VCU instantly commands zero torque in under 500 milliseconds, just like the hardware rules dictate.
So HIL is the ultimate bridge. It takes the mathematical assumptions from the left side of the V and validates them against the worst-case scenarios on the right side, without risking the car or the team's safety. It ensures the software and hardware safety systems actually function as one.
Phase 7, the Test Readiness Review, or TRR, is the final gate. Strategically, this should be treated as a mandatory, full-scale scrutineering simulation done in your own workshop. You absolutely cannot wait until the competition to find a flaw. If you find it there, your schedule is blown.
Let's run through the critical pre-race safety tests that have to be simulated during TRR. First, the basics, the tilt test.
The tilt test verifies two things. First, the car is inclined 45 degrees, and you check for any fluid leaks, coolant, brake fluid, no leaks allowed. Then, it's inclined to 60 degrees to verify stability. No wheel is allowed to leave the ground. It requires building a simple homemade rig, but it verifies basic handling stability before you start high-speed testing.
Next up, the test that is the bane of every EV team's existence, the one that makes everyone nervous, the dreaded rain test.
Ah, yes. The rain test is a true test of your CDR discipline. The team has to simulate 2 minutes of continuous heavy spraying while the HV system is fully energized. The critical requirement is that the insulation monitoring device, the IMD, must not trip the alarm and cut power.
I've heard so many stories of teams working perfectly for months, only to fail this test because of one tiny overlooked cable gland or a connector seal.
Those stories are 100% accurate. You realize, standing there with the hose, that sealing decisions aren't just about water. They're about preventing a high-voltage flashover that could end your competition instantly. This test forces design integrity all the way back to the CDR stage. If your connectors and seals aren't IP65 rated or better, you will fail this test.
And finally, verifying the system under the massive dynamic loads it'll see on track, the brake test.
For the brake test, the car accelerates to over 30 miles per hour. Then the driver executes a hard stop, locking all 4 wheels. The HV system must remain active and fault-free during that massive structural shock load. This verifies the stability of the entire HV structure, confirms the accumulator mountings are secure, and proves the wire harnesses are safe under the highest inertia forces the car will ever see. If anything breaks here, you have a critical late-stage failure to fix.
Okay, we've verified structural and electrical safety. Now we prepare for dynamic ops. The rules mandate the ready-to-drive sound, the RTDS.
The RTDS is critical for track personnel. When the car enters drive mode, a sound has to be emitted for 1 to 3 seconds, over 80 dBA, to warn people the vehicle is energized and ready to move silently. And a critical note from the rules. You are explicitly forbidden from using songs or animal noises. It has to be simple and identifiable. Use a decibel meter during TRR to confirm loudness.
Now we're finally ready for physical validation, the dynamic testing protocol following the classic crawl, walk, run philosophy.
Exactly. Start small. Phase 1 is the crawl, the jack-up test. Wheels off the ground, low-speed run, just verifying basic control, motor encoder signals, and rotation. Phase 2, the walk, is skid pad and figure 8 testing at slow to medium speeds. This checks basic handling and suspension without pushing the limits.
And then the run.
Phase 3 is the run. straight line acceleration, gradually increasing power from 20% to 100%, meticulously monitoring battery voltage drop and motor temperatures. We're looking for thermal runaway or aggressive battery voltage sag under high current.
The ultimate check on the entire design and the final validation of the energy strategy is the endurance simulation.
This is the final exam. It verifies the entire V-model effort. The team has to run a continuous 22-kilometer session. The purpose is twofold. First, validating the thermal management system over a sustained period. Does the motor overheat on kilometer 15? Second, collecting comprehensive energy consumption data. Using data loggers like Motec or Vector, we collect state of charge data and temperatures to optimize the final control strategy. This data closes the loop.
And that data closure is the critical final step in the V model. The testing data collected on the track, the real-world current draw, the actual thermal performance, it has to be used to correlate and update that digital twin model we created back in CDR.
Precisely.
You're saying if our model predicted a motor temp of 85 degrees after 10 kilometers, but the real data shows 95, we have to go back and fix the model.
Exactly. If the track data deviates by more than, say, 10% from the simulation, the underlying physical assumptions in our model, be it cable resistance, aero drag, whatever, they must be corrected. This correlation is the fundamental closed-loop iteration the V model enforces. It ensures knowledge is preserved, and the team learns exactly where their initial estimates were wrong, setting a much better baseline for next season.
This entire journey, guided by the V model, leads us to the ultimate strategic mandate for a new team, especially in year one. To finish first, you must first finish.
That's it.
So let's recap the 3 core pillars that underpin success for a new team based on this deep dive.
Pillar 1, absolute rule compliance. Passing the ESF and SES is priority number 1, no compromises. Pillar 2, design simplicity. Choose the single motor rear-wheel drive, use stable materials like steel or aluminum, and opt for cylindrical cells. And Pillar 3, obsessive validation. Reserve at least 50% of your total development time for HIL and physical track validation. Testing has to be prioritized over manufacturing speed or looks.
So the V model transforms that engineering instinct, that urge to just build a faster part into reliable competitive performance. It forces teams to think about verification at the design stage and to mitigate failure before they even start manufacturing. It's fundamentally an anti-risk engineering process.
It creates a predictable path in a very unpredictable competition. We're building robustness, not just speed.
The V model proved that reliability wins in the rookie year, but next year, if they hit that 100-kilometer metric, they face a new challenge, maximizing performance. And the jump from their reliable 400V 2WD system to a cutting-edge 600V 4WD torque vectoring setup is enormous. What part of their current design, that single motor, those simple electronics, becomes their biggest liability when they try to double the voltage and quadruple the complexity next season? That's the strategic problem the V model forces them to start solving today.
The liability will be the hardware and the lack of a high-fidelity 600V testing capability. The key to making that jump to 600V and complex 4WD is proving the control software is fail-safe at those higher voltages and with those complex dynamics. They have to prioritize building out their HL system this year to include high-fidelity thermal and electrical models capable of accurately simulating transient current spikes and component degradation at 600V. They need to understand what components must be upgraded. That verified high-fidelity simulation platform is the prerequisite for safely designing the high-voltage hardware and complex controllers for 4WD. If they start designing the next-gen HL now, they'll have the tools they need to manage that massive leap in risk next year.